show you my hair, and so you wouldn't feel so bad about what's going on. I haven't worn anything with a collar in a month, and I'm ready to do some thermochemistry. So let's go ahead and get on with it. 3 weeks. We got 3 weeks till the AP exam. More than enough time. You just want to make sure that you leave yourself enough time to polish up the stuff you need to polish with. Make sure you get enough sleep, and I'm sure you'll do well. Remember, we'll be doing this for the next 3 Thursdays. Next week is the last unit and some test study tips, and then we'll have some Q&A. So if you're really struggling over a concept, then feel free to contact Matt at A+ College Ready and let him know those topics, and we'll be happy to help you out with your questions. I do have a couple things to show the teachers real quick, and so teachers, if I can get you to look on Canvas at some point, and on Canvas there is a shareable equation sheet. There is a shareable equation sheet 2020. And this is just something that I saw on Facebook, but it's a try at taking the existing reference sheet and adding a bunch of stuff to it. So in preparation for a talk that we're going to have with a bunch of teachers, so in preparation for a meeting, my screen was going wacky, that we're gonna have with a bunch of teachers next week, just be thinking about what's good about that sheet and what's bad about that sheet and how we can add to it. All right, and then students, if I can talk to you and your teachers for just a moment, I wanted to show y'all that there's an awful lot of stuff out there, and I'm assuming that you know a lot of this stuff already, but just so that I know what you guys know, I just want y'all to know that on YouTube, there's actually a channel called the A+ College Ready Science Channel, and it's got biology, physics, and chemistry reviews. Now, my goal here is not to teach you everything in the world about thermochemistry. If you were to look at the thermochemistry videos provided by AP, and that's part of that, and those videos are part of the A+ College Ready playlist for chemistry. If you were to look at those, they have done a ton of pre-response questions already. So I have on purpose left those out, and I've also left out the kinetics ones that they've done. There's no need to redo them. So on top of this, you really need to go back and look at the ones over kinetics and the ones over thermochemistry, right? Who doesn't like a cute cat when you're going? If y'all have questions at all today, feel free to put them in the chat bar. And when you put them in the chat bar, we will know what everyone thinks. And if you have any questions, if I'm going too fast or you just can't hear me whatsoever. Right? And teachers, if you see questions pop up in the chat bar that I don't hit, feel free to answer them with all your content knowledge. So you really only have 5 different types of thermochemistry problems you'll see in the FAQs on May the 14th. Calorimetry, so Q equals MCAT. Heats of formation, Hess's law. Bond energy, bonds broken minus bonds formed. And then looking at an energy diagram, how can you tell if a reaction is endothermic or exothermic, positive delta H or negative delta H? And as always, those Maxwell-Boltzmann distributions, which talk about how fast are molecules going. So let's just go ahead and get into it. So this is the first question. This is not a bad one. I could see them doing part of it and asking a bunch of other questions along with it. So we're going to burn some alcohol. The alcohol gets burned underneath water. So you may have done a lab similar to this where you burn Cheetos or some other food underneath a can full of water. And the way they determine how much alcohol gets burned is they weighed it before and they weighed it after. So The data tells you how much got burned, how much of the water got heated, and how much the temperature of the water changed. So calculate the magnitude. The first thing I want y'all to notice is the word magnitude, and hopefully when y'all came in, you had some sense of what magnitude meant, but the word magnitude just means size. They don't want a positive or negative sign anywhere. They just want a number. So you wouldn't say I lost -5 pounds. You just lost 5 pounds. You gained 5 pounds. Magnitude is just the number. Then based on the experimental data, how much heat in kilojoule is released. And if we look up at the equation, they've given us a balanced equation already. So it's nothing we need to worry about doing. This is only about thermochemistry. So let's see how you would attack this and where you would earn points. So we know to find kilojoules or joules, it's going to be one of 4 things. It's going to be bond energy. They didn't give us bond energies. It's going to be heats of formation, which they didn't give us any data for that either. It's going to be Hess's law, where we add up equations like a keep or flip thing. They didn't do that. Or it's going to be calorimetry. If I had to guess for the AP exam, I'm going to guess that they have a calorimetry problem. So that's how this one works. Notice that they tell you the heat needs to be in kilojoules. So that's what we're going to do, is we're going to work our way towards kilojoules. So it's Q is equal to MCAT. Now, what mass do you use? The mass is always the mass of the thing that heats up. So go back. Where's all that heat going? It's going into the water. So we're measuring the temperature of the water, so we want the mass of the water. So that 125 grams is the mass of the thing heating up. Sometimes students get confused and they're like, oh, should I add the mass of the alcohol to the mass of the water? No, you have to put the mass of the thing that's changing temperature. If you had added a solid to water and stirred it up, then you would take the water and the solid together. This 4.18, okay, I am so sorry. Let's try this again. Hopefully y'all got to eat some of that snack while you were going.
And Danny, I did try sharing my screen and it worked, so it's got to be something, I guess, on your end. It looks like it's working.
No, it's as soon as I turn on my camera for any amount of time, I think my face breaks the computer, because it was showing that it was sharing a screen, but everything was black. So I just turned it off and came back on, and
looks good now.
So y'all, you look good now. Okay, all right. I'll just try to keep my face away from the camera then. All right. Well, let's go back to the beginning then. All right. So this is the problem. We're burning some alcohol. You can see the bottles of alcohol this time. The alcohol is burning and that heat is going into the water. They tell you the mass of the alcohol that was combusted. They tell you the mass of the water that was needed, and then how much the temperature of the water went up. So looking at the problem itself, it says calculate the magnitude of the heat energy. And again, that word magnitude just means a number, not a plus or minus number, just a number. Right? And then how much heat in kilojoules is released. So this is where you earn the points. So hopefully this gets us back on track. We're trying to calculate kilojoules, and Q is equal to MCAT. I have the mass of the water, 125 grams. The 4.18 is a constant given to us either in the problem itself or oftentimes on that reference sheet. And the 51.1 minus 22.0 is the temperature change, right? So notice when you do that, what unit you're going to come out with, you're actually going to come out with a unit there of joules. So the unit right there in joules tells us, don't just throw down kilojoules because you're feeling excited about it. Let the problem tell you what the units are going to be. And that comes out to be 15,200 joules or 15.2 kilojoules. So maybe on your exam reference sheet, maybe you want to remind yourself that Q is equal to MCAT comes out in joules. That would be a good thing to write down. And maybe you need to write down that there are 1,000 joules in a kilojoule. Just think of what would help you answer these questions better. All right, based on the experimental data, if 1 mole is combusted, how much heat in kilojoules is released? this is a fancy way of saying what is the delta H, but we know it's released, so it's negative. So it's how many kilojoules per mole. Well, what you just found was the number of kilojoules. So in part B, all they're asking you to do is find the number of moles of alcohol. I apologize. Someone downstairs is having a conversation. And all we have to do is take the number of moles of alcohol and divide the number of kilojoules by that number of moles. And boom, we get this answer, 1661. Now, keep in mind that anywhere in the AP questions, you could actually have a sig fig problem. So always think to look at your numbers, and they rounded it to 2 here because of the 0.55 grams of the alcohol is your thing that decides the limiting amount of, sorry, the 0.55 is 2 sig figs, and that decides how many sig figs you get. So that was actually a pretty easy problem. Find Q, divide it by moles to get kilojoules per mole. Here's another problem. Now, this is from a really long time ago, and this is one of those problems that was just all thermochemistry all the time. I don't think on this year's exam, they're going to give you this problem in this entirety, but they totally could give you, like, what kind of equation is this? Oh, it's acid base. And then they might even have you draw a Lewis structure or something like that. Or they might say, what's the best piece of glassware to use, like they did in this problem. So the student selects 2 100 milliliter beakers, uses them to measure out hydrochloric acid and sodium hydroxide, and measures their initial temperature. Then they pour them into an insulated cup. You may have used a styrofoam cup just like this. And once they add them together, they get to a final temperature of 29.9. Is this enough information to determine the enthalpy of reaction? So enthalpy is delta H. And is it enough to go to 2 sig figs? So for enthalpy, that's going to be delta H is kilojoules per mole. So look over the information. Do you know enough information where you can find delta H? And then list 2 specific changes to the experiment that will allow the student to determine the enthalpy of reaction to a precision of 3 sig figs. So what they gave you may be not good enough. What would you do to give you a little bit more in the way of sig figs, right? Then somebody else is given 2 solutions. They mix them together. They calculate the heat to be 4.1 kilojoules. Calculate the student's experimental value for the enthalpy in kilojoules per mole. Well, they gave you the kilojoules, so letter B, part I, is really just asking you to, again, take that kilojoules and divide it by moles. So you've got to look up at the reaction itself and think about the stoichiometry of which one is the limiting reactant. Then it comes down to talk about the student assumes that the thermometer and calorimeter don't absorb energy during the reaction. Does this give you a slightly higher value, lower value, or the same value if you had taken the thermometer and calorimeter into account? So in other words, if we're assuming that the cup doesn't absorb any heat, then what happens? And then one assumption in interpreting the results is that the acid-base reaction goes to completion. Justify this in terms of equilibrium. Now, we'll be doing equilibrium next week, but I just kind of want to show you how they're mixing in questions together. So let's see how they would actually go about solving this problem. Is the experimental design enough? No. If you're using beakers to measure out solutions, then you're not going to be getting a very accurate reading. So remember, the choices were Erlenmeyer flasks, beakers, and graduated cylinders, and it tells you their precision, or how good they are. So was it good enough? No. So you got to make your claim. your evidence is the data that's there, and then reasoning is a very, very short about that's just not good enough in order to get a 2 sig fig answer. What 2 changes would you make that will allow the student to actually determine it to 3 sig figs? Easy enough. Use the graduated cylinders, which are much more accurate and much more precise. And then you can go ahead and get to 3 sig figs. You could also use a stronger acid and a stronger base. And instead of just getting a little bit of a temperature change, it would give you a bigger temperature change. So if you look at it, it started at 24.5, ended at 29.9. When you subtract those two, that's only going to give you a 5.4 degree difference. That's only 2 sig figs. So how could you make it where the temperature change gave you more significant figures? The idea is we just use a stronger acid, a stronger base. And if you did that, then you would get a much greater temperature change. Now, notice you couldn't just say use more of the acid and more of the base, because if you did that, you'd have more liquid getting warmer. So you can't say, oh man, the temperature, if I just used more acid and more base, not just stronger, then you'll also have more water. It's not going to get appreciably warmer. So let's get down to the thermochemistry itself. So we had to find the limiting reactant. And the truth is, both of them are limiting. They were both 1 molar, and they were both 75 milliliters. So you could use either one to figure out this problem of how many moles of reactant were used. So they did the math going from mils to moles. And then they just took the number of kilojoules divided by the number of moles, and they got an answer of 55 kilojoules per mole. Okay, so the student calculates the amount of heat to be 4.1. That part was given to us. Calculate the values, experimental value for the enthalpy of reaction. So the question becomes, why is this answer down here negative? Why did they put negative 4.1? Well, the important thing to remember when you're doing delta H problems is a positive delta H is endothermic, and it makes things colder. It absorbs energy from the surroundings. A negative delta H is something that releases energy, releases heat, and makes the surroundings warmer. So we actually saw the solution get warmer from 25 degrees to 29 degrees. So remember, delta H is both a number and a sign. So just kind of remember to tell yourself, okay, I got to put down a number, and I have to think of what that sign is. All right, let's see what else is it asking us to do. The student assumes that the thermometer and calorimeter do not absorb energy. Would that make the calculated value higher, lower, or the same? Well, the best way to miss this question is not to answer it at all. So if you get to this point and you're not sure, give it some thought and then think, I'm just going to go out there, I'm going to try. So the calculated value would be lower than it would have been if they had been taken into account. So the thermometer and the calorimeter do actually absorb some heat. So if you're saying not only is the heat the amount that the water gained, but also some of it went into the calorimeter and thermometer, then that would actually cause a little bit of change from what we would have done if we had just said, no, it doesn't matter at all. One assumption is interpreting the results of the experiment that it goes to completion. Now, if unit 9 or unit 8, sorry, acids and bases was actually a part of the exam this year, this would be a fair question. But if they ask this question, this is still a valid question if they give you a value for K. So let's look and see what the value of K is. So let's say that they gave you this equation, that water turns into H ions and OH ions. That's actually called the KW on your exam reference sheet. So they could give you this equation and ask you that and say, here's a K value. Well, what do? Well, this is not an acid and a base turning into water. This is a water turning into an acid and a base. So what do we do when we have to flip the equation? When we flip the equation, we take the K and we invert it. So instead of being 1 times 10 to the negative 14th, the K for the flipped equation would be 1 times 10 to the positive 14th. So if we go back to the question, one assumption is that it goes to completion. Justify this in terms of equilibrium. Well, if the K value is 1 times 10 to the 14th, that's a really big number. And a really big number, a number greater than 1, is something that we can say, aha, that's something I know how to do. And we can actually, sorry, my bad. A number greater than 1 goes to completion, right? So any K that's greater than 1 automatically goes to completion. I mean, that reaction is, the K is so big that it will go pretty much all the way to completion. All right, I'm going to skip the last part in order to go back. If you remember from last week when Ms. Brown was talking to y'all, she talked about intermolecular forces. And this is one of those questions that's going to fold in a lot of the stuff you saw before. So here's the 2 molecules they're about to talk about. Lauric acid and sucrose. Which compound is more soluble in water? So you ought to be able to look at the structures and decide which one is going to have more opportunities for binding with water. And hopefully you came up with sucrose. So you reviewed last week, you brought that in, you get a point. Assume that a 1.5 gram sample is burned and all the heat goes into water. Calculate the final temperature of the water if the delta H is negative 37 kilojoules per gram and the specific heat of water is 4.18. So in other words, they're giving you all the data you need. They want you to find the final temperature, the delta H. So let's look and see how we would do that. So you know that it's 37 kilojoules for every gram, and you had 1.5 grams. So if you did the math there, you get that there's a total of 56 kilojoules released when you burn the lauric acid. So that becomes our Q. That's the amount of energy that was released. If we plug that into Q is equal to MCAT, we know that the 56 kilojoules gets changed to joules. The 325 grams is the mass of the water. We don't use the mass of the water and the lauric acid because we didn't mix the lauric acid with the water. It's not that the 2 of them together heated up. It's that the lauric acid was burned, just like the alcohol in the previous problem, and all that heat goes into the sample of water. So I plug what I know into Q equals MCAT, and I solve for delta T, and delta T comes out to be 41 degrees. So if the change in temperature was 41 degrees, and they want to know the final temperature, then all we have to know is what temperature did we start at. So we started at 25 degrees, and the temperature changed 41 degrees. Now, did it go up by 41 or down by 41? Well, you know the delta H is negative, and it tells you that the heat energy is released. Both of those are clues that this solution should be getting warmer because it's an exothermic reaction. So we take the initial 25 degrees, we add in the 41 degrees that was the change in temperature, and we get 66. And look, 2 points, done. In an attempt to determine the delta H experimentally, a student places a 1.5 gram sample of lauric acid in a ceramic dish underneath an aluminum can. So maybe something you did in a lab at school. The student ignites the sample with a match and records the highest temperature reached by the water in the can. The experiment is then repeated, but this time it's made of copper. The specific heat of copper is 0.39, and the specific heat of aluminum is 0.9. So, what does the specific heat have to do with how much the temperature changes? Well, specific heat is a function of how much energy does it take to make 1 gram of it go up 1 degree Kelvin or Celsius. So the lower the specific heat, the bigger the temperature change is. The greater the specific heat, the less temperature change there will be. So just keep in mind, the greater the specific heat, the more energy it takes to make it change temperature. So take a piece of aluminum, throw it outside on a hot sunny day, take the same mass of water, put it out there for the same amount of time, you will notice that the aluminum gets hotter a lot faster. So let's see if we can figure that out. That's a claim evidence reasoning because it asks which one will it be? Will the copper be greater than, less than, or equal to the aluminum? So if we look at where we have the answers, the temperature will be greater in the can made of copper. That totally jives with what we said. Since the copper has a lower specific heat, it has a bigger temperature change. All right. In both the experiments, it was observed that the measured final temperature of the water was less than the final temperature calculated in part B. Identify one source of experimental error that may account for this and explain why the error would make the measured final temperature of the water lower. Well, if you've ever cooked at home, or if you did this lab where you burned a Cheeto or something like that underneath a can of water, then you know some of that heat was lost. So if we assume that all the heat went into the can, then it's just not right. Some of the heat got lost to the environment. So the water didn't warm up as much. That would be one source. And the year that this question came out, this was the most popular answer. Not all the heat from burning it actually went into the water. And you also could have made the argument about heat got into the can or the thermometer. Not all of it went into the water. Or maybe not all the lauric acid burned. Like if you burned your Cheeto, you might go, oh, there was some stuff left behind, right? So all these things are possible, and they took any of those possible answers, and they actually gave you 1 point for the source of the error, and then 1 point for an explanation. So when you get to a problem like this, always take a stab at it. The best way to miss a problem is not to answer it whatsoever. All right, for this one, I'm going to let you think on it, part A and B for a minute. So let's give you a minute and a half, and I'll let you think about what would be the answer for A based on what you saw last week, and then how would you go about solving for B? So that's close to a minute and a half. Looking at the two molecules, hopefully you saw that the one on the left, glycerol, can hydrogen bond because it's got a hydrogen stuck to oxygen, and it could be hydrogen bonded to the O on another glycerol molecule. They both have LDFs because they both have electrons. And the one on the right will create dipole-dipole forces. So you could name, as long as you name both molecules and which ones they had, then you could talk about why does glycerol have a higher boiling point? And that should be because, hey, I can make hydrogen bonds as a glycerol molecule and trichloropropane can't. So you can point out that you know about intermolecular forces. But then notice all of a sudden it jumps right into a calorimetry problem. The reason why I mentioned before I thought it would be calorimetry is Lord knows if you look at the AP exam, as long as I have, most all of the delta H problems involve some type of calorimetry. So let's see what they've given us and see if we can figure out what's going on. They told us the delta H for the whole equation. What mass of glycerol would need to be combusted to heat 500 grams from 20 to 100 if we know the specific heat? Again, this isn't bond energy because they didn't give us that. It's not Hess's law because they didn't give us equations. And they didn't worry about giving us any kind of bond energy or heats of formation or anything like that. So we have the C value, the specific heat, we have the change in temperature, and we have the mass of the water. And if you notice that that's enough to find Q. So if you can find Q, find Q. So let's see how they did this. They plugged in the Q of the water. So it was 500 grams, again, just the mass of the water, times the 4.18, times the 80-degree change in temperature. And they get an answer of 167 kilojoules. Now, is that enough that we can go from kilojoules to what mass of glycerol? Well, look at the other information they're telling us. We know it's that many kilojoules for every 1 mole. And we know how many kilojoules there are. So we ought to be able to link the two of those facts together and go from the kilojoules that were released and using that fact for glycerol to go to moles of glycerol. So there's the number of kilojoules. There's the delta H value for glycerol. This is the molar mass of glycerol, and they tell you that up here in the problem. And you come out with 9.30 grams of glycerol. So again, we had to go from the heat we found, negative 167 from MCAT, and the number of kilojoules per mole. You make sure units cancel, and then you use the molar mass to go to grams. And that was it. A little bit of intermolecular forces and then a calorimetry problem. All right, now let's see if this one is a calorimetry problem. If you think this is a calorimetry problem, I think you have problems, because if you look at this, there is no mass of something, there is no C value, and there is no change in temperature. So if you had to guess between Hess's law, where you're adding together equations, and heats of formation, which is what it says, and bond energy, then you should have come up with heats of formation. Now, if you looked on your reference sheet, then all you would have to do is go over to your reference sheet, and it tells you that delta H, when you're using heats of formation, is all of the products, so everything over here, minus all of the reactants, right? So we're going to take the silver, which doesn't appear down here, and multiply it by 3. So how are we supposed to know what the delta H of formation of silver is? Any element in its standard state, so just an element all by itself, automatically has a delta H of 0. So we're going to take 3 times 0 and 4 times HNO3, which is given to us there, And then we're going to subtract it from 3 of those, 1 of those in the balanced equation, and 2 of those. So if we did all of the math, blue minus the red, then we should be able to find the delta H of reaction. And if you look, that's exactly what they did. 3 of the AgNO3, because there's 3 of them, and you took the 90 and the negative 286, and you subtracted out the HNO3s. Now, they didn't put silver in there because silver is 0, but you totally could have done that. So all the products minus all the reactants. The trick here was remembering that you had to multiply by 3, by 2, and by 4. A lot of people forget to do that. So just make yourself a note. Make sure you multiply the heat of formation by the number in the balanced equation. Now, this part is interesting. This is not anything to do with thermochemistry. So how am I supposed to come up with something that lets me isolate silver nitrate from the other products? The student runs a reaction using a 3 to 4 mole ratio. How are we supposed to get the silver nitrate out? Well, all they're asking you for is, how can you make the silver nitrate precipitate out? How can you make it form a solid? Because everything else is going to be aqueous. So what can we add to this to make sure that the silver actually precipitates out? You could add a chloride to it doing that, or you can evaporate the water and you'll leave behind solid silver nitrate. So those are your choices there, but you also could have added something where you added some chloride solution somewhere, or something that you knew was going to make it precipitate out. You never know when they're going to ask you a question and then peg something on the end of it that has nothing to do with thermochemistry. Don't freak out. Just take a guess. What can you do to get it to get that answer right, to get that point? All right, here's an equation. They dissolve the urea in water to make 5 milliliters of a saturated solution. So calculate concentration in moles per liter. Well, that's going to be pretty easy. Take the number of moles. They gave you grams. They gave you molar mass. Find moles, divide it by liters. And again, you may need to write down somewhere for the AP exam that 1,000 milliliters are in 1 liter. All right, so that part would be pretty easy. I'm not going to go over that. You ought to be able to find concentration, molarity. All right. They also determined the concentration is 19.8 molar. Based on this information, is the solution dissolution endothermic or exothermic? All right. Well, so if we look at the correct answer was 17.9 molar, right? So if you go back and look at the equation, then this was 17.9 molar when it all dissolved. So when you up the temperature, when you go from 25 degrees to from 20 degrees, sorry, to 25 degrees, it goes from 17.9 molar to 19.8 molar. So when you heat it up, you get more dissolved. So that becomes a Le Chatelier thing. So again, we're seeing this mixing of things. Of here's a thermochemistry problem, here's an equilibrium problem, and here's a stoichiometry problem. So think about which way would cause this thing to shift to the right to give you more stuff dissolved. And so again, the dissolution is endothermic or exothermic. You would make a claim. You would give your evidence that it became more concentrated. And then you would say, if energy is a reactant and you add more energy, you should get more product. Something like that, right? You're going to be able to answer that question pretty quickly, jump on it. However, if you don't find yourself sweating it, because on this particular year, there's going to be a lot of things to do, and we need y'all to do all the things you can do first. So if you got to part D and you're like, I don't even know what to do, leave yourself several lines, come down here and do part E. right? Now, I think this is the kind of question you'll see this year. This year, they told us that, yes, you can hand write out those answers. They also told us this year that you could type out your answers. Well, doing math on a computer is hard, so they could give you something like this and ask, what are the specific measurements that are required to be made during the experiment? Okay, it wants the molar heat of solution. So it wants to know the number of kilojoules. Y'all remember my handwriting. Miss Brown thought hers was bad, but nothing like mine. Is the number of kilojoules per mole. So what measurements do we need in order to make that happen? Well, we need to know moles. How are we going to know moles of urea? Well, to know moles of urea, we've got to know grams of urea. So we need to know the mass of the urea. Done. Okay. We need to know the mass of the water because that's going to be the urea and the water warm up. And we need to know the change in temperature of that solution. So those are the measurements that we need to make. So let's see what they said when they were handing out points. You need to know the mass of the urea to find moles. You need to know the mass of the water. You need to know the temperature of the water in the beginning and the temperature of the water at the end. So that's a way of them giving you a calorimetry problem without them actually having you do the math. Right? This is a very short one. And I thought, they could do this year because this seems like a very, very easy question as long as you know what's going on. According to the diagram, is it exothermic or endothermic? Justify your answer. So again, this is claim, evidence, reasoning. So the first words out of your pencil are going to be exo or endo. And since you start way up high and end way down low, we know you're losing energy. Losing energy is exothermic. You end up at a lower energy state than what you started at, and that would be your justification. And then they add in this extra little bit. Manganese dioxide is an insoluble substance that can be a catalyst. So draw a curve to represent the reaction as it occurs in the presence of manganese dioxide. Well, if you're typing your answers, you're not going to be able to do that. And this is actually a kinetics question. So what could they do? Well, what if they gave you several different lines? What if they said there's an original line, that one's supposed to be higher, and there's another line above it? Which one of those is the curve that represents what it looks like in the presence of a catalyst? And the catalyst would just be this dotted line because it wouldn't go up as high. Because remember, from where you are to the top of the hill represents your activation energy. So that's a way that they would mix those in. And y'all can see where you could answer very, very quickly. Boom, this is exothermic because you end up with less energy than what you started with. And the dotted line would be with a catalyst. That would be a very quick way to test your knowledge. This is one I just made up. Right? And this is going to be a mixture of what Miss Brown did last week, where is the O2 oxidized or reduced? Justify your answer in terms of oxidation numbers. When it was combusted, the volume was 28 liters, temperature and atmospheres. Again, Miss Brown went over some of the gas stoichiometry with you. And then determine the amount of heat in kilojoules. If you look, they're doing 2 or 3 units all at one time. And this is probably what you're going to see. So is the O2 oxidized or reduced? Let's take a look. Well, oxygen has an oxidation number of 0. It's an element all by itself. In water, oxygen has an oxidation state of -2. Whenever you get more negative, that means you gained electrons. And since you gained electrons, that's reduction. So same stuff she went over last week. Oxidation is losing electrons, reduction is gaining. When a sample is combusted, the volume of CO2 was 28.0 liters. They give you a temperature and a pressure find moles. Well, from that, you ought to be thinking, wait, I know. This is a pervert question. PV equals nRT. You know the pressure is 1.23. You know the liters was 28. This R value down here comes from your reference sheet. And the temperature here, Kelvin, came from your 22 degrees Celsius. Because remember, the units have to match. The Kelvin here has to match with the Kelvin there. So remember to look at units. Units are very important. So if I did this math, I would come out with 1.42 moles. So that gives me an answer for B. Determine the grams of C3H7 that was used. Well, I know moles of CO2. It's asking me to find grams of alcohol, of propanol. So all I have to do is go from moles of CO2 to grams. That's just a stoichiometry problem. So I would just work my answer, 1.42 moles, use my mole to mole ratio from the balanced equation, use the molar mass of alcohol, and boom, you would get the answer 28.5 grams. Determine the amount of heat in kilojoules that was released by the combustion reaction. So notice, here's the delta H up here. It tells you when this reaction happens, it's negative 4042 kilojoules per mole. So you just found how many grams of C3H7OH there were from the moles of CO2. So we just need to do a little bit more stoichiometry. We can either work from grams of the alcohol to kilojoules, or you can work from moles of CO2 to the kilojoules. Me personally, I'm lazy, so I worked from moles of CO2 to kilojoules. Now, where did I get the 4042 and the 6 from? Well, if you go back to your balanced equation, when 6 moles of CO2 reacts or is formed, I get 4042 kilojoules produced. That's where that fact comes from. So this just becomes a stoichiometry problem and a stoichiometry problem. And then it says, oh, by the way, we did this in a room full of air. They're telling you the initial temperature of the air. They're telling you the specific heat of the air. And they're telling you the mass of the air. So hopefully at home, you're jumping up and down and going, oh, MCAT, MCAT, MCAT. So all we have to do is plug in what we know. Normally they do water, but for this time they decided to do air. So how would we go about solving this? The Q is equal to MCAT. The Q is here. That was given to us in the problem. That was the answer we found before. My bad. The 674 times 10 to the 5th is the mass given to us in the problem. The specific heat is given to us in the problem, and we're looking for the delta T. Now, the delta T was 1.41, but realize that is the change in temperature, not the final temperature. Delta H is negative, which means this is going to warm up. So if the temperature started at 22 and only got warmer, you would get a final temperature of 23.41. So notice that they mixed, what kind of reaction is this? With, hey, here's a gas law. Here's a little bit of stoichiometry. Here's a little bit of stoichiometry using delta H. Boom, now circle that back around to do calorimetry. In all the other problems we've done so far, we start with the calorimetry and we work our way over. This one is just a reverse of that. Just always be thinking, okay, with what I have, how can I find what I need? All right, so the rest of these are kinetics. So if you want to see some more delta H problems worked, I would go over to the College Board's thing done by Michael Faribaugh and the other guy who I can't remember who it is. And I would look at that video because he does a lot more examples of FRQs having to do with thermochemistry. In fact, he took a bunch of the ones I was going to do. I know that's not cool to say, but he took my answer. So the half-life of the catalyzed reaction represented above was measured under various conditions. The reaction is first order. Explain how the data in the table is consistent with first order. So if you don't remember, go back and watch the kinetics thing that I did before for A+ College Ready. But the thing to remember, the very important thing, is that for a first order reaction, the half-life is constant. And if you look at these three trials, as long as temperature doesn't change, then the half-life should stay the same. So the half-life for this thing was 100 seconds every single time. So when the half-life is constant, that means it has to be first order. Calculate the rate constant for the reaction at 350 degrees. Include appropriate units. So if you go over to your reference sheet, you'll see this equation down here where you want to plug in your half-life of 100 seconds and just solve for K. And remember, since it's 0.693 over 100 seconds, the unit is in inverse seconds. So they just want you to plug into that formula and solve for K. Boom. Right? Is the initial rate of the reaction in trial 1 greater than, less than, or equal to the initial rate in trial 2? Well, now you have to look at trial 1 and trial 2. Temperature is the same, volume's the same. The pressure is different. So what could make the pressure difference? In trial 2, the greater pressure is because there's more molecules. In other words, there's more of the cis-2 butene. And whenever we have a greater concentration of reactants, the reaction goes faster. So who's got a faster rate of reaction, trial 1 or trial 2? Well, trial 2, because it's got a greater concentration, would be faster than trial 1. So you would just, first words out of your pen would be trial 1 is less than trial 2. That's your claim. Then you have to justify your answer, because basically you're saying that the concentration is different, so the pressure is different. The half-life of 4 is less than the half-life in trial 1. Explain why in terms of activation energy. So half-life is how long does it take for half of it to disappear? Well, in trial 4, we have a higher temperature. If you have a higher temperature, what does that mean? That means more of the molecules are going faster. There's still some going hardly any at all, but there's a lot more molecules going faster. And so if there's a lot more molecules going faster, then more molecules have enough energy to overcome activation energy. So imagine a situation where you make $1 a week, and to get into a movie, it costs $2. Now, you're not going to be able to get in without saving up. But imagine that all of your friends, some of them got paid more and some of them got paid less. Some of them would be able to go, and some of them definitely, just like you, would not be able to go. But let's say that everybody got a raise. Let's say that everybody, on average, excuse me, got more money. Well, overall, the higher average amount of pay that you got would enable more people to go to a movie, assuming that movie theaters were open then. So just like the higher average temperature increases the energy, the average energy of all the molecules, more of the molecules would have enough energy to overcome that activation energy, right? So you don't say, oh, hey, a higher temperature lowers the activation energy. That ain't true. It's all about how many of the molecules have enough energy to overcome the activation energy barrier, right? If they're going to ask a kinetics question this year, and I got to believe that they will, acid base is huge and electrochem is pretty big. and delta S and delta G are huge. So the fact that they left those off, I've got to think there's going to be either a problem where they ask you to look at some data and tell you what order it is, but they could also ask you this graph question. So here's 3 questions. One of concentration versus time, natural log of concentration versus time, and 1 over concentration. If you looked on your exam reference sheet, then what you're going to see is concentration versus time. If it was straight, it would be 0th order. Natural log of concentration is what we call the first order integrated rate law. So it would be first order if this one was straight. And 1 over concentration is the second order integrated rate law. So just based on your reference sheet, they go 0, 1, 2. And they were nice enough in this problem to go 0, 1, 2. Well, which one is straight? Well, that one looks straight-ish, but if you notice, there's a little bit of curve to the natural log, whereas 1 over the concentration is exactly straight. So the question says, determine the order of the reaction. Notice what's missing right here. Justify or explain. They don't want your justification. They don't want your explanation. So don't worry with spending time trying to do that. Just come in here and say second order. Boom, done. The initial rate is 0.001 moles per liter second. Calculate K. So if we go and say, okay, how do you write a rate law? Well, rate law is rate is equal to K times the reactants. And in this case, we made it squared because we determined that it was second order. So rate is equal to K times the reactants squared because it's second order. So go back to the problem. The problem tells you, well, here's the rate. What is the initial concentration? Well, if you looked at the initial concentration of trial 1 is this open circle. The initial concentration was 0.02. So they told us the rate. They told us the initial concentration for trial 1. This comes down to, can you read this graph and find trial 1? Knowing that as you go down here, trial 1 ends up on the bottom and trial 2 on top. Just notice that they're talking about trial 1. So all you have to do is plug in the information and find K. And again, let the units tell you what the units of K are. That's all it wants you to do. All right, so we run this experiment. The ions slowly react. It reaches a constant value of 0.0174. Here's the rate law right here. The value of the rate constant was determined to be 9 times 10 to the negative 4th. They're giving us all kinds of information. Calculate the rate of the forward reaction after 600 minutes. Include units with your answer. Now, go back to your reference sheet and find the first order integrated rate law. We know it's first order because down here, it talks about here's the rate law, and there's a 1 right there that they don't type in, but it says 1. And they tell you the value for K. So how can we plug this information in to the first order integrated rate law? Well, here's the first order integrated rate law. Sorry, not the first order integrated rate law, my bad. No, I skipped part A. That's me. Sorry. No, that's right. You know what? I'm confusing myself. Calculate the rate of the forward reaction after 600 minutes. So at 600 minutes, what is the rate? It's asking you to look up here and see that this is a value of 0.0174. So I just made this way harder than it is. They give you the rate law. You know the amount of BF4 they give you the value for K. Sorry for leading you astray. They're telling you what to plug in to find your answer. I still don't think I did that right. So let me move on before I embarrass myself further. So this is one I wanted you to see just so you could make some guess as to what they're going to have you do. This is not really a math problem right now. They're telling you the rate is K times CONH22. So they're saying it's first order. So if it's first order, explain how the data supports the proposed rate law. Well, again, remember what I told you. You can look for a graph with a straight line. But this is not a straight line. So if you really wanted to waste some time, then you could go, oh, I'm going to do the natural log graph, and I'm going to do 1 over graph. I'm going to do 3 graphs and see which one's straight. No need to do that. Okay. What I want you to notice is how long does it take for half of it to disappear? So we started at 0.1 and we got to 0.5 after 10 hours. And then from 0.05 to 0.025 down here was another 10 hours. So what did we say when the half-life is constant? What we knew is that when the half-life is constant, we know that that's first order. If you didn't want to use the graph, you can say, this is where I started at. This is when half of it was present. This is when another half was present. Explain how the data supports it. A constant half-life is a sign of a first order reaction. Using the proposed rate law and the student's results, find the value of K with units. Now, you're just going to have to get used to seeing that K with units is something they're going to be asking for. So let's see how they actually found that answer. We plug in the half-life of 10 hours, same as we did before, and the 0.693 is given to us in the equation for half-life, and when you solve for that, you get 0.069. Now this time it's inverse hours, but again, let the units do the talking for you. You also could have done it this way using the first order integrated rate law. What they did was they plugged in the initial value of 0.1. They plugged in the value at 10 hours, and they just solved for K. Trust me, this is easier. So the student learns that it was run at a pH of 13. Well, now this year, they're not really asking you to do anything with pH. So they might want you to say that it was run at a really high concentration of OH. They could say that. Describe an experiment, including the initial conditions that you would change and the data you would gather to determine whether the rate of the reaction depends on the concentration of OH. So what could we change in this thing to give us what could we change in this experiment? We could just not do it at a pH of 13. Let's do it at a different OH concentration. And what is the data I would need to gather? I would need to gather how quickly the reactant goes away or how quickly the product gets made. And if that rate of reaction changes, then that would tell me that, yes, it depends on OH. So basically, you're just saying, ooh, let me just pick a different OH concentration, and then let me try to see what the rate would be based on either how much reactant goes away or how much product gets made. Right? Here's one more. And if you look, they're giving you a chart that's not a straight line. They're giving you the question that the data is consistent with the rate law of K1 times O3. Based on the graph, determine the half-life. Well, the half-life is how long does it take for half of it to disappear? So what's half? of 1 times 10 to the negative fifth. Well, half of 1 times 10 to the negative fifth is 5 times 10 to the negative sixth. So what is the half-life? And that half-life would be 0.01 seconds. If you notice, there's also a half-life here where you go from 5 times 10 to the negative sixth to 2.5 times 10 to the negative sixth, and it would also be 0.01 seconds. So far so good. Determine the value of K. Well, we know that it's first order because this is the rate law and there's an imaginary 1 next to the O3. So all we have to do is go over to our half-life equation and do 0.693 divided by the 0.01 seconds. So you got 1 point for the correct value, 1 point for the correct unit. You'll notice that this whole idea of using a graph and half-life being constant comes up again and again and again. And so if you see that, it's something to look out for, because that's something that you totally could answer without doing a lot of math. The half-life is constant, first order. Considering the concentrations of the reactants, is this also an OK rate law? Okay. Now, this is something that comes up sometimes, and if you were lucky enough to do the lab of crystal violet with your teacher, there's way more O3 than there is of the HSO3. Oh, sorry, way less of the O3 than there is of the HSO3. The HSO3 is almost, let's see, 64 times concentrated, more concentrated than the O3. So are these two rate laws, this one right up here, we would call it a pseudo rate law, is that the same thing as this rate law down here? Well, yes, because the HSO3 is just not doing anything. It's so concentrated that some of it's going away, but it's just not enough to matter. So let's go back to that job you had, right? So you're making $1 a week. If someone were to take 50 cents away from you a week, that would be a big deal. But you might have a friend who makes $100 a week, and if somebody takes 50 cents away from them a week, it's not that big a deal. So what's happening in here, this O3 is changing a lot, and the HSO3 is hardly changing at all. So since the HSO3 is pretty much staying constant, we kind of just ignore it here in this rate law. We just say that HSO3 isn't changing very much, so yeah, that would be fine. Okay. So hopefully that gives you some idea of the types of questions they're going to be asking you on these AP on this AP exam. I got one more for you, and then we'll go on. So this is a really, really old one, but I found it and I thought, oh, perfect. Determine the order of the decomposition reaction. All right, well, you guys go ahead and take 30 seconds and see if you can figure out what order it is just based on the graph. All right, close enough. If you guessed half-life, you're right. Because if you look, it took 8 seconds for half of it to disappear, and then it took another 8 seconds for the next half of it to disappear. Constant half-life, first order, boom, done. Then they give you some data and a chart, and it says, write a rate law. Well, how do you know what to write the rate law on? We always write the rate law on the slow step. How do you know which one will be the slow step? It tells you. This is the slow step. Done. So the rate law is going to be rate is equal to K times the concentration of the reactant. And when you have elementary steps, the coefficient of 1 in front of the Cl2 becomes the exponent. So to write our rate law, half-life is constant, has to be first order. The slow step would be this, boom. Last part, a student claims that Cl2 is a catalyst. Explain why it's false. In other words, you don't have to make a claim. They tell you the student's wrong. Your job is to explain why they're wrong. Well, a catalyst is something that starts out in a chemical reaction and would get regenerated at the very end of the chemical reaction. So it's something there in the beginning, something there at the very end, and that's a catalyst. But the Cl2 doesn't show up again. The Cl2 is actually broken down in the steps of the chemical reaction. That means it's not a catalyst. They also could have said something like Cl was an intermediate, or they could have asked you, what is Cl? Well, Cl would be an intermediate, something that's made in the middle and is used up in the middle, and C5H9 would also have been an intermediate. So that's another type of question that they could have asked you. Now, that's a lot, and if you're still here, I applaud you for sticking around. So just a couple words of wisdom for you before I go. I just need y'all to realize you got this. You got 3 weeks to get ready for this exam, and I know you're totally going to rock it. So go back to that A+ College Ready YouTube account and look that over. Your teachers are going to be working with you to make sure that you've got all the information you need. I would say, why don't you try writing out some answers on paper? Why don't you try typing some answers out on a computer, see what works best for you? And the other thing I'm seeing in message boards, teachers and students, is maybe instead of just taking pictures, maybe try this 2 apps, either Adobe Scan or Cam Scanner. Try those either in the, not iTunes, the App Store for an OS thing, or you could look in the Google Play Store. Both of them are free, I believe, but just try that. You want to find one that lets you take a picture of your work and get it up there cleanly. So, any questions? Anybody? Well, thank you so much, y'all, for coming. We appreciate you spending some time with us.